Good morning, everybody. This is Miss Maneely, and I'm going to go through a tutorial with you to help you understand some basic probability rules and to help you with some of the problems from your homework so that you're ready for your test on Tuesday and Wednesday. I'm going to start just with a quick review of some basic probability rules. We talked in class the other day about what we call the general addition rule. Remember that with addition, we're always talking about the probability of event A or B. So the addition rule always goes with the word or. So try to remember that. Addition always goes with the word or. So anytime I want to find the probability of events A or B, I'm going to be thinking about the general addition rule. So let's take a look real quick at this Venn diagram. And I've noticed that I have two Venn diagrams because we have two different situations. We have situations where A and B overlap, like they do in this first one. And notice they overlap, and that overlap area is what we refer to as A and B. And then in the second Venn diagram, notice that A and B do not overlap. When events do not overlap, we call them disjoint, or sometimes we refer to them as being mutually exclusive. And if you think, disjoint means not joined, mutually exclusive, imagine like an exclusive group where you don't include everybody. So there's a different formula for each of these scenarios. So let's talk in general. In general, we'll talk about events that overlap. And so if I'm trying to find the probability of A or B, I'm looking at, and let me see if this will work. So I'm looking at basically, let me get a highlighter here. I'm looking at the probability of event A, which is this whole area in here. That would be the probability of event A. And then I also want to include the area for the probability of B. Problem is, notice that I've counted that center area twice. So in general, for the addition rule, I need to be careful. I need to basically, I'm going to be taking the probability of event A, and I'm going to be adding it to the probability of event B. But because when they overlap, I end up adding that area twice, I also need to subtract the probability of A and B. And that is what we call the general addition rule. Now, if the two events don't overlap, then I can simply add the probability of A to the probability of B because the probability of A and B is simply 0. If there's no overlap, then the probability of A and B is simply 0. And so for disjoint events, did I spell that right? Whoops. For disjoint events, the probability simply becomes the probability of A plus the probability of B. And if I were to subtract the probability of A and B, it's simply 0. And so I can just leave it as the probability of A plus the probability of B. And that would be for disjoint events only. So if there's ever an overlap, I have to make sure that I subtract it because otherwise I'm going to count it twice. Now, conditional probability is a little bit different. Conditional probability basically says that, so let me start it over here. The probability of A given some event B, and this is the notation I use. Okay, this means the probability of A given event B. And so if I want to find that, that basically is going to be the same as the probability of both A and B divided by the probability that B occurred. We're not going to be using this formula very often because the conditional probabilities that we're going to be looking at are actually going to be in the form of a two-way table. And if we have a two-way table, this formula really isn't necessary, and I'll show you some examples of the homework. The other rule is the multiplication rule. And with multiplication, you'll usually see the word and. So remember, with the addition rule, we're using the word or. With the multiplication rule, you're going to see the word and. So if I wanted to find the probability of events A and B, Well, that's going to just be equal to the probability of event A occurring times the probability of event B, given that A occurred. And so now I'm referring back to my conditional probability formula. And that would be the general multiplication rule. We also talked last class about what we call independence. And if two events are independent, it changes both the conditional probability and the general multiplication rule. So let me use a different pen to kind of talk about that. So if events A and B are independent, and basically what that means is the probability of A is not going to influence the likelihood of B occurring. I spelled that wrong. I spelled that right. So if A and B are independent, then the probability of A given B, well, it's not going to matter if B occurs or not. If they're independent events, then the probability of A given B is simply going to stay the probability of A. And likewise, with the general multiplication rule, if my two events are independent, and you'll usually either be told in the problem that they're independent, or you'll be able to tell. For example, like flipping a coin over and over and over again. It doesn't matter if I flip a coin, 6 times and get heads every time. When I flip it the next time, the probability of getting heads is the same as it was before. It's still 0.5. That would be independence. But think about drawing cards from a deck. If I draw 3 cards from a deck and I put them back and reshuffle the deck, right, then the likelihood of getting a heart on the first draw would be 1/4. If I put the card back and shuffle, then the likelihood of me drawing another heart is still going to be 1/4. And then if I put it back and shuffle, draw again, it's still going to be 1/4. However, if I don't put the cards back, I'm reducing the number of hearts every time I draw a card, and so the probabilities will change. By not replacing the cards in the deck, I don't have independence. And so that's when I would have to use these general rules over here. But if the events are independent, then the conditional probability rule looks like this. The probability of A given B is simply the probability of A. And the general multiplication rule basically says then the probability of A and B is simply the probability of A times the probability of B. And so these formulas I think will make a little bit more sense when we start doing some practice problems. But right now, these are the basic rules. You will be provided with these rules on the test. You'll be provided, I should say, with the general rules. You do need to understand what independence and mutually exclusive or disjoint events look like. Okay? And I am going to apologize. My dog is with me as I'm doing this tutorial, and she is seeing that I'm talking, and she's thinking I'm talking to her. So she may start talking back to me. I don't know if you can hear her, but this is Stella. You'll hear me talking about her a lot this semester. Okay, so let's take a look at this first example. It says government data assign a single cause of death that occurs in the United States. The data show that the probability that a randomly chosen death was due to cardiovascular disease or heart disease is 22%. And the probability that it was due to cancer was 22%. I don't know if I just said those probabilities right. My dog is distracting me. So 48% is due to heart disease, 22% due to cancer. Now, because we have this single cause of death, let's change to a pen. Because we have a single cause of death, I know that my events must be disjoint. So if I wanted to draw a Venn diagram, I'm just going to do this by hand, and I apologize. I'm not using my smartboard. I'm using this little slate notebook thing, and it's a little bit harder to write on. But if I wanted to have an event for heart disease and an event for, what was the other one, cancer. So this would be heart, this would be cancer. And actually I drew them wrong because we know since there's a single cause of death, no one can die of heart disease and cancer. So the coroner will only, shoot. Let me just start that over again. All right, so let me start this over again. So if we have a single cause of death, that means that they're not going to overlap. So here's my heart disease, here's my cancer, There's no overlap. So if I want to find some of the answers here, so in part A, it says, what is the probability that the death was due either to cardiovascular disease or cancer? So I'm pretty much finding, remember, either means or, so the probability of heart disease or cancer. Well, if I use my Venn diagram, I can actually go ahead and plug the probabilities into my graph. So it tells me that 48% is due to cardiovascular, so that's going to be, or heart disease, that's what I labeled as H. So 0.48 is going to go here, and then we know 22% goes to cancer. And so if I wanted to know the probability of either heart disease or cancer, I'm basically looking at the area in both of those circles. So I'm going to add them together. So 0.48 plus 0.22. And I can do that on my calculator. Let me just, so 0.48 plus 0.22, and we get 70%. All right, so if I wanted to, I could also use my formula. So the general addition rule, remember, refers to my OR event. Since we had disjoint events, I would simply add the two probabilities together, which is essentially what we did with this Venn diagram. We simply added the probability of heart disease to cancer. And then what about in letter B? It says, what is the probability that the death was due to some other cause? Well, some other cause is this area out here. And remember, the Venn diagram is just another way of illustrating a sample space or a probability model. And if you remember, in order to have a valid probability model, your probabilities have to add up to 1. So we already know that these two circles together add up to 70%. That means that the area on the outside of these two circles must be 1 minus 70%, or 30%. So using the Venn diagram, I can find the probability that the death was due to some other cause. And the way I would just write this would just be to say the probability of not the event A or C, or I'm sorry, H or C. And that would simply be 1 minus 0.7. That's our complement rule. And that's going to be 0.3. In the next problem, it says in number 2, real estate ads suggest that 64% of homes for sale have garages, 21% have swimming pools, and 17% have both features. As soon as I know that there's a probability of both, I know that this is a situation where my events overlap. And so let me see if I can do this a little bit neater using some of my, let's see. So, all right, so that looks a little neater than me writing by hand. But if in this case, let's go ahead and use the letter G to represent a garage and P to represent swimming pool. So here's my G, here's my P. Now here's where I have to be careful, because if I start assigning probabilities the way they're listed in the problem, I would be tempted to put 64% here, and 21% here, and 17% in the middle. But if I do that, look what happens. If I do 0.64 plus 0.17 plus what was that, 21? I can't even read my own writing. 21, I get over 100%. And we're not allowed to have over 100% because this has to represent our entire probability model, our entire sample space. So the reason that it went over is because I counted the 17% twice. So if I'm labeling this circle as my circle that represents all my garage outcomes, so it also is going to include that overlap that includes people that also have a pool. So I actually have to subtract away the 17%. So what I need to do is erase the 64 and erase the 21 and subtract those away. So the people that have just a garage, or what we would say is a garage only, which would be this area here, a garage only, would be the 64% that have the garage minus that overlap, that 17% that also have a pool. And so 47% have a garage only and no pool. I'm going to have to do the same to figure out the likelihood of finding someone with just a pool and no garage. So I know that 21% have a swimming pool. Oops. I needed to subtract away the 17% that also have a garage, and that leaves me with 4% that have just a swimming pool. So if I wanted to find the following probabilities, I can use my Venn diagram. The only thing is I need to complete my Venn diagram. Remember, the Venn diagram is another way to express a probability model, And I haven't looked at all of my possible outcomes. I know that center area is both. So this would be the garage and pool. This is supposed to be a G. And then this outer area here would be neither. And in order to find the value or the probability that a family would have neither, it might help to go ahead and add up all these probabilities and then subtract them from 1. So 47% with just a garage, 17% with both a garage and a pool, and 4% of people that have just a pool leaves me with 68%. If I do 1 minus that probability, I can do second enter or second answer, so I don't have to type that in again, I find that 32% have neither. So now I've constructed a Venn diagram that shows all of the possible outcomes, and so now I can actually start finding probabilities. In part B, it says, what's the probability that a home for sale has a pool or a garage? So the probability of pool or garage, using the Venn diagram, it's going to be, let's see if I can use a highlighter here, would be this whole area in here. All of this stuff is going to be your pool your pool or a garage. And so simply all I need to do is add the probabilities together. So this would be, oops, 0.47 plus 0.17 plus 0.04. And we already did that. We said that was 0.68. Now, I can find those probabilities using the Venn diagram. You can also find this probability using your general addition rule, which would tell me to take the probability of A plus the probability of B and then subtract the probability of both. And so if I look back at my problem, it tells me the probability of a garage is 64%. The probability of a pool is 21%, and the probability of a garage and a pool, oops, it's supposed to be a P, is 17%. So if I wanted to, I could find the same formula, or I could find the same probability using my probability rule, but it's going to look different. Because if I use my probability rule, that tells me to take the probability of P plus the probability of G minus the probability of P and G, which would be 0.64, because now I'm looking at the entire probability of having a garage, not just a garage only, but this entire circle, which has to add up to 64%, plus the probability of having a pool. But because I end up counting the overlap twice, I have to subtract it away. And again, if you add this all up, if we take 0.64 plus 0.21, and we subtract that 17%, we get the same thing, 68%. So you can do this problem 2 different ways. You can use a Venn diagram, or you can use your probability rule for the general addition rule. Letter C says, what's the probability that a home for sale has neither a pool or a garage? So that would be the probability of not what we did up here, pool or garage. And remember, a not statement is a complement. So I would just take 1 minus the probability of P or G, which we said was 68%, and that gives us 32%. Now that's using the rule. I could also just refer back to the Venn diagram where I already calculated that probability. And then letter D says, what is the probability that a home for sale has a pool but no garage? So that is simply referring to this area here where we have a pool but no garage. And I think probably in this case, it's a lot easier just to visualize this with the Venn diagram. And so the way I would actually express this would be the probability of a pool and no or not garage. And using the Venn diagram is easy. It's just going to be 4%. And so that's how you would calculate all those probabilities. And again, you can use a Venn diagram or your formulas to help you with those answers. All right. In number 3, this is basically giving you a 2-way table where we basically did a survey of 200 members of a health club. So I know that the total here is going to be 200. And we're asked to find some probabilities. If we were to select someone at random from the health club, what's the likelihood that they're a single woman, a divorced man, a widow, and so forth. Before we can find those values, what would help is if we find all the totals in the table. So I'm actually going to pause this for a second and calculate those totals, so you don't have to watch me actually add them in. So I'm actually going to pause for a second and find those totals. Okay, so I found all the totals for the table. I added the rows together, I added the columns together, and that gave me the total for each row, each column. And I did double check to make sure everything added up to 200. You do often want to double check to make sure that you didn't add wrong somewhere, just to make sure that your totals are what they're supposed to be. So now once you have your totals, it makes it a little bit easier to find the probability. So we're basically asked, what is the probability that a club member selected at random will be a single woman? So if I'm interested in single women, I'm looking out of the entire group, what are the odds of picking a single woman? So if I go into my table, I can actually search for my single, here's my single category, and if I go over to women, I know that 26 members of this particular group were single women. If I want to know the probability, then I'm going to take that 26 and I'm going to divide it by the total in my group, which is 200. And I'm not going to work, well, I guess I can go ahead and divide that. So 26 divided by 200 leaves you with a probability of 13%, or 0.13. If I want to find the probability of a divorced man, then I'm simply going to go down find my divorced category and identify the number of men that are also divorced. So this would be man and divorced. If I were trying to find if I were writing this using proper notation, so this would be the probability of man and divorced. And I would basically say that there are 21 divorced men. And remember, to find a probability, you have to divide by the total, and in this case, the total is the whole group, which is 200. And so if I take 21 and I divide that by 200, I get about 10.5%. And if I want to go back up here, this is the probability of being single and a woman. So both criteria are met. That's the probability we found. All right, in the next one, it's just asking about a widow. So it could be a man or a woman. So if I'm looking at the probability of being a widow, I have to identify all of the widows. So if I look at the widows, I know that there are a total of 10 of them. So the probability of being a widow, there's just one criteria here. Oops, I'm writing window. The probability of being a widow is just going to be 10 out of 200. And again, if I do this on my calculator, 10 divided by 200 is 0.05. So 5% of the group are widows. And what about a man? Well, now it doesn't matter what category they fall under. I'm looking at all of the men, and there are 117 of them out of the 200. So the probability of being a man, we said, was 117. 117 out of 200. And let's see, 117 divided by 200 is 0.585. So it looks like there are a little bit more men than women. And we can see that from the totals. There were 117 men and only 83 women. Okay? And so the final question basically asks, are the events widow and man independent? And then we're asked to explain. So let's go back real fast to that first page with some of our rules where we talked about independence. Since I'm not dealing with any conditional probabilities in that example, there was nothing that said, if you know that you've picked a man, what's the probability that it's a widow? But we did look at some of these types of probabilities, the probability of being a man and a widow. And if we can verify that the probability of being a man and a widow is the same as the probability of being a man times being a widow, if those two numbers are the same, then we can have independence. So this is the formula that I'm going to use to see if those two events are independent. So what I want to do is I'm basically asking the question, is the probability of being a man and a widow equal to the probability of being a man times the probability of being a widow. Now, we've actually found all of these probabilities. Probability of being a man and a widow, we found was 0.105. So we know that. And then on the other side, if I look at the probability of being a man, we said that was 0.585. And the probability of being a widow, we said is 0.05. Well, let's see. What happens when I multiply 0.585 times 0.05? I get 0.02925, which is clearly not the same as 0.105. And so since these probabilities are not the same, then these events are not independent. And it sort of makes sense. If you think about it, if you think about gender and becoming a widow, I would sort of suspect that there are more women widows than male widows, simply because in terms of lifespan, men's lifespan tends to be a little bit shorter than women's. And so I would think that there would be some influence in gender and whether or not an individual is a widow. So it makes sense that these two events are not independent. But this is how you would show it mathematically. And there is a problem like this on the test. So remember your rules and then just look to see, because in the question, you might have already found the probabilities. The question would be then, are they the same? Are they equal? And that's how you would explain it. All right, in the next problem, you're given a probability distribution. And I know it's a probability distribution because it tells me, but that also means that all of these probabilities should add up to 1. And just to be on the safe side, I'm actually going to try it out. So 0.22 plus 0.15 plus 0.08 plus, whoops, what did I do here? Plus 0.07 plus 0.07 plus 0.41. There we go. I verified that it is a probability distribution. All my probabilities add up to 1. And now, here's the question now. It says, in a given year, there were 250 home fires. It says to use the probability distribution to estimate the number of home fires. So I'm not looking to find the probability this time. I'm finding the number of home fires. So if I'm looking at 200 home fires, or 250 home fires, what's the likelihood, or how many were caused by cooking? Well, I know overall 15% are caused by cooking. And I know some people set this up as a proportion, basically saying that we know that 15%, that's the same as 15 out of 100. So you could set this up as a proportion. 15 out of 100 would equal what out of 250? And if you cross multiply, that would be 100x is equal to whatever 15, let's see, that's 15 times 250. That would be 3,750. And then if we divide both sides by 100, we would get 37.5 home fires on average out of 250 would be caused by cooking. Another way to calculate this that I think is just a little bit easier, if you think of, I'm basically trying to figure out what 15% of 250 is. And of in math generally refers to multiplication. So another way of doing this would simply be to take that 15% and multiply it by 250 home fires, because I'm looking at 15% of 250. And so if we go back to the calculator, 15% times 250 gives you 3750. So either way you do it, you get the same value. It's about 37.5 home fires. And it's okay that it's a decimal because it's just an approximation. So we could say about 37.5 home fires are caused by cooking. If I wanted to know the number that were caused by the electrical system, then I'm going to just find in the problem 8%. So I'm going to do 0.08 times 250. And 0.08 times 250 means that there were about 20 home fires that were caused by a problem in the electrical system. So notice in letter C now it's saying not caused by smoking. So if you think about it, if I wanted to find the probability of the fire not being caused by smoking, that's not how it's identified in the table. So I'm going to have to use my complement rule here. The probability of not being caused by smoking would be 1 minus the probability that it was caused by smoking. And the probability of smoking is 7%. So that's 93%. So 93% of the fires were not caused by smoking. So if I take 0.93 times 250, that'll give me the number of fires. So 0.93 times 250 is a lot of them. That's going to be 232.5 of the fires were not caused by smoking. And then in letter D, fires that were caused either by heating or appliances. Well, remember, since this is a complete probability distribution, I know there's no overlap, so I can simply add those two probabilities together. So I'm basically looking at heating system or appliances would be the 22% or 7%. So if I add those two together, I'm going to keep them separate, but 0.22 plus 7%, and if I multiply that by 250, that means that there were about, oops, I didn't do that right. So it's 0.22 plus 0.07 times 250. Okay, so that's better. So 72.5 were caused either by the heating system or by appliances. And then the last one says that they were caused by someone either cooking or smoking. And so again, I have to go back up to look at cooking was 15%, smoking was 7%, and so and then if I multiply that by 250, and go back to my calculator, that's about 55 fires that were caused either by cooking or smoking. There we go. All right, and then we have, I think this is the last one. In number 5, it says the teacher assigns a worksheet for homework after 83% of her lessons and bookwork the rest of the time. Her records indicate that 92% of the students complete a worksheet when assigned, and only 48% complete the workbook, or I'm sorry, the bookwork when assigned. So the question is, ultimately, we're going to be constructing a tree diagram to illustrate the situation and then determine the probability that a randomly selected student completed the homework assignment. So in this case, I have a sequence of events. We have the teacher assigning homework, and then we have this whether or not the students actually complete it. So instead of doing a Venn diagram here, it's actually when it's a sequence of events, it's a little bit easier to understand if we do a Venn diagram. And with the Venn diagram, we have two options for the first stage in the sequence. So the first stage is is the type of assignment that has been assigned to students. And so we've got a worksheet, and we've got bookwork. Okay. Okay. And then from there, either the students complete it or they don't. And so for each of these, I'd have another stage in my Venn diagram. Oops. So if I assign a worksheet, either they're going to do it or they don't. Oh my goodness, why isn't this working? Same with the bookwork. Either they're going to do it or they don't. And so I'm going to also identify the outcome for each of these branches. So this would be complete, and this would be do not complete. They're either going to complete it or they're not going to complete it. Okay, and so with the tree diagram, we also want to assign probabilities. And so what I'm going to do is go back to the problem and look and see what it says about the worksheet. It says that the teacher assigns a worksheet for homework 83% of the time. So if I'm going to do the 83% of the time, I'm going to put that here on my tree diagram. So it's going to go, the probability goes along the branch. So a worksheet occurs 83% of the time, and the rest of the time is bookwork. That must mean that these two events are complements of each other. So to figure out the likelihood of me assigning bookwork, or the teacher assigning bookwork, I do 1 minus 0.83. And that's going to leave me with 17%. So 17% of the time the teacher assigns something out of the book. And then we have the next stage, either the kids complete it or they don't. And so it says, her records indicate that 92% of students complete a worksheet. So let's go on the worksheet branch. And it says that 92%, so I'm going to put the 92%, doesn't really look like a 9, does it? I'm going to put the 92% here along this branch. Well, that means that the rest don't complete it. And so again, I'm looking at these two events being complements of each other. So if 92% complete the worksheet, that means that 8% don't. And that's just 1 minus 0.92. But I also assign bookwork. And so I also want to look at the percentage of students that complete the bookwork. Well, only 48% complete the bookwork. So this is going to be 0.48%. And that must mean that I said it right, but I didn't write it right. So 48% complete the bookwork. That means 52% do not. So that would be my completed tree diagram. It shows both stages of the events, all of the possible outcomes, and it assigns probabilities to everything. So let's take a look at the next question. It says, what's the probability that a randomly selected students completed the homework assignment? So I'm just looking at the probability that they completed it. It doesn't mention whether or not it was a worksheet or bookwork, so I'm going to assume that they mean it could be either. So I'm going to look back at my tree diagram, and what I notice is that they could have completed the worksheet using this branch or this branch. And so if I'm looking at the probability of completing the of assigning the worksheet and completing it, this is an and statement, worksheet and complete. And so remember, with an and statement, we multiply. So I multiply along this branch. So I'm going to do 0.83 times 0.92. But that's not the only avenue that I could get to have a completed homework assignment. It could be this avenue or the other avenue. And so an or statement, we said we're going to add. So I multiply along the branch and then add the branches together. So to find the probability of assigning bookwork and having it completed, I'm going to multiply 17% times 48. And so if I complete this on my calculator, so we're going to have 0.83 times 0.92 plus 0.17 times 0.48. And that means, all in all, 84.5, whoops, I didn't need to put the decimal there. So basically that means that 0.8452, or about 84.5% of students complete their homework, whether it's a worksheet or bookwork. This is how you would complete the tree diagram. Okay, and so what you need to know for the test, obviously, like the problems that we've assigned for homework are very similar to the test questions, so you're going to have to do problems like this on the test. But let's do another example of a tree diagram. I'm thinking off the top of my head, but let's say I'm just going to call them event A. This would be event not A. And let's say event A occurs 30% of the time. That means not A would occur 70% of the time. And then let's say after event A, we could have event B, or whatever the complement of B is. And so let's say the likelihood of getting to B would be 0.4, and this would have to be 0.6, because each branch has to be complements of each other. And then here we have the same thing, B or not B. But let's say this time this is going to be 0.8 and this is 0.2. Well, if I wanted to find the probability, let's say, of not B, I'm going to look at all of the avenues that it would take me to get there. So let me do a highlighter this time. So to get to not be, we're talking about this outcome and this outcome. So that means that I could follow this branch, or I could follow this branch. And so to find the probability, remember we multiply along the branch, so it's going to be 0.3 times 0.6, and then we add the two branches together, 0.7 times 0.2. So that would be plus 0.7 times 0.2, so 32% of the time. Okay, so that's just another quick example of how to do a tree diagram. I hope this was helpful. If you have questions, please have them ready when you come in so that I can go over them. And I wish you good luck.